let us begin. So we are in the middle of this shortest path single source algorithm. So here the question is, you are given a directed graph with positive edge weights. So these are like roads between cities, and there is a central vertex called S, which is the source vertex, and from there you want to calculate all distances, shortest possible. So delta SV is the shortest distance, and PSV is one of the paths which has this unique shortest distance. So BFS solves this for the weight function 1. Now we want to solve it in general. So we have made multiple observations. First is that it makes sense to find the nearest city from S. So this vertex in the picture V2 is the nearest one. So that distance we know when we begin this algorithm. And based on that, there is a process we saw, which is this blue theorem in the left bottom, that is the connection between old graph and new graph G prime. What are the distances there? So we can see that actually distances, shortest distances don't change. So delta G SV is the same as delta G prime SV for all the remaining vertices, other than S and the nearest U. Okay, so this already gives an algorithm, but we want to improve on that, and also we want a more elegant structure related to shortest path. So we'll now continue and we'll use this lemma that we proved, which says that in any shortest path, the subpaths are also shortest. Okay, so shortest paths are closed under subpaths. So namely, if S to Si is the shortest path, then the vertex just before that, called Sj, that also is the shortest path from S. Right? And here we use the property that weights are positive, or in other words, weights cannot be negative. So it's like driving from S to Si via a city Sj. So when you reach Sj, you want that route to be shortest also. If that was not shortest, then you will use the shortest and you will get a contradiction. So that is basically the proof. Or the other case is that S to Si is just a direct edge, in which case that's the base case. In every other case, there will be an Sj in the middle, that is shortest. Any questions? So what this lemma or this property of subpaths tells you is that there is a shortest paths tree. So the idea that we will now, this will be visible in a while. So the next idea is to have better control on the structure via this shortest paths tree. That we can build incrementally. So just like in BFS, DFS, it helps to understand the algorithm when thinking in terms of a tree. Here also we'll think of the shortest paths tree, which is based on that lemma. So what the lemma is saying is that this single source S vertex, this is your S0. So remember, we are ordering all the other vertices from according to the distance from S. So there is S0, S1, S2, dot, dot, Sn minus 1. So what are the interconnections between them? So the connections are basically like a tree. So you have S0 to S1 an edge, which is the S1 is the nearest vertex from S. Then from there we have found some S2, from where we have found some S3, and then S4 may not be in that path, S4 may be somewhere else. Okay, this may also happen. It is not that you travel from S0 to S1 to S3, then you reach S4. Maybe the path to S4 is completely different, so that's a different branch of the tree. Then S5 may come back in this path, so S5 may be here. And S6 may be somewhere deeper here. And S7 may go back here. Okay, so this can be completely arbitrary, but it's still a tree. So we are only looking at these edges, which give you the shortest path. So shortest paths form a tree, and then the rest. So when I say incrementally, so the idea is that the algorithm finds first S0, then it finds S1. So that part of the tree becomes visible. Okay, that is discovered, and then S2 has to be found. So how is S2 found? So for that we will use a temporary tree structure stored. Let's say we store it up to S4. That is what we have computed till now. Okay, so S0, S1, S2, S3, S4 has been calculated, let's say. So then how is S5 found out? How do you discover S5? That part, outside the blue part, is still undiscovered. So that would be your induction step or iterative step in the algorithm, right? What is that step? How do you go from, how do you keep growing this shortest path tree? That is the question. So any ideas? How to grow T? So you should do the same thing that you did in the very beginning, which was S0. Right? What you did with S0 was you found the nearest city from S0. So the same idea you should now abstract out at the level of this blue tree. So what should you do? You should find the vertex U, which is nearest to the tree. Okay, so think of this S0 to S4 like a mega vertex. What is the nearest city from this mega city? So that is your U that you want to find, S5, right? So the formula will be as follows. So Si is the vertex U in the set U, which is the set of undiscovered vertices. That are closest, or that is closest So this is the idea. We'll give the formula in the next slide. So you have discovered S0 to Si minus 1. So that part of the tree, like S0 to S4, has been discovered. From there you want to go to S5. So you want to go to Si. So what is Si? You don't know that. So this Si we will pick to be the one that is closest to the current tree T. Okay, and the formula for that is that is SI should minimize, or U should minimize, that is U minimizes the distances from the tree. So what is this distance formula from the tree? So essentially you pick a j, go from S to Sj. So pick a j which is less than I, because you only know distances up to I minus 1, j equal to I minus 1, right? So you use those distances, so go from S to Sj, and then from there you should, where should you go from Sj? The vertex U where you want to, which you want to find the distance to. So you go from Sj to U, which is the weight function. So what is happening here in the diagram is in this tree T, you have S0 and you have Sj. So you drive to Sj, and then from Sj you go out to the vertex that currently you want to check. Right? So the U are the unexplored ones. So this is what you want to find the distance from the tree. And right, so just try this for all the U's, for all the Sj's which are connected to U by an edge. Okay, so you have to minimize this expression. Is this clear? So full statement is that once you have reached Si minus 1 in your shortest path, the Si will be chosen as the vertex U that is nearest to the tree, which means that this expression, so you go from S0 to Sj, that the distance you know, and you add the edge weight from Sj to U, this should be minimized. Right? So basically you are driving within the tree and then you are jumping out to U. So by this kind of driving, what is the closest to U? So that's the distance delta Tu, and you minimize that, and then that is the vertex which I will call Si. This will be the ith nearest vertex from S0. Is this fine? So proof of this, once this expression is given to you, it's not, proof is quite simple. So this U is this vertex U, which is in the set U, which is basically from the vertex remove the tree. So this vertex small u is nearest to the current tree T. So just like we had deduced before that from S0 the nearest city, if it is U, if it is S1, then we know exactly the distance from S0 to S1, right? So using the same kind of an argument you get from this observation that the nearest distance from S0 to this U is exactly this the formula we just calculated, we just wrote. So I mean, you can complete this this proof. The point is that if there is some other way to reach U, So you can look at the vertex, which is the last vertex of T that you are going out from. Okay, so you will have this S0 to Sj, and then there are few more edges which are going out before you reach U. And that different path will actually give you a contradiction to delta TU definition. So at this point, you should try to complete the proof. Okay, but intuitively it is quite clear that this should be the case. So once you have this intuitive expression, you can now give the pseudocode. Okay, so shortest paths will be found by drawing this tree, starting from S0. So, so this now, this function delta U can be used to write down Dijkstra's algorithm for single source shortest path. Okay, so this is one of the most famous algorithms in computer science. It is more than, it's around 70 years old. And this is used without naming it everywhere. So all your, I mean, in Google Maps, or when you are somewhere, you are trying to find the nearest hotel or nearest restaurant or whatever, everything to do with the distances will of course use this algorithm, shortest paths algorithm, and also in situations which are other than roads and transportation, like communication, or there is a circuit that you want to design for the motherboard. So there also you have to draw wires between the various accessories. So all those things, again, somewhere Dijkstra algorithm will be used. So the snippet of Dijkstra algorithm is as follows. So you are given a graph and S, and well, graph is given with the weight function. So what you do is the set U, which is the undiscovered part, that initially is everything. Initialize it to that, so the tree is empty. And you can initialize for vertices small u, delta U to be. So initially, what is the distance from the tree? So everywhere it will be unknown, right? So unknown is infinity, unreachable kind of. So this, set this to infinity for all the vertices, small u. And then let us start introducing the initial, we grow the tree. So we grow it by setting delta S to 0 and putting S in T. Well, okay, we will put it in the for loop. So we'll now do the for loop. Over all the vertices 1 to n. So let y be the vertex that we were looking for here. In the formula, we wanted a vertex that is minimizing delta. So we'll call it y in the pseudocode. So y is the vertex in the undiscovered vertices with min delta function that minimizes the delta function. And so delta from S to distance from S to Y will be this value. So delta in the implementation, by the way, is an array. So this, when you want to extract the min value, is array enough, or can you think of a better data structure for this? Yeah, you should use a heap, and automatically min heap. So delta is a heap. So you should keep this as an array physically, but the augmentation on the array is the heap structure. So basically Y is doing extract min on the heap, and that now leads to the discovery of a vertex which is outside the tree, and so we can grow the tree. So we move Y from U to T. And then what? What should be the next step in the pseudocode? So you have discovered Y, it is moved inside the tree, and what do you want to do next? Should we end the for loop? Yeah, so why should we do that? Mm-hmm. Yeah. So what he's suggesting for efficiency purposes, in fact, even for correctness purposes, is see the definition of delta function depends on the tree, right? So there is an implicit. You don't need to write it in the C program, but this always depends on what the tree is, right? So delta actually depends on the tree. Now suddenly in this step you have changed the tree. So once you change the tree, the delta array should also change, right? So that is what we should do next. So since T changes, we need to edit delta array also. So how do we edit it? So for that, we have to basically see which of the locations in delta array need an update. So that is decided by basically the neighbors of Y. Okay, so we'll do that. We'll only go over those locations. So for all U, with Y comma U and edge, what you want to do is the following. You want to update that locations in that location of the delta heap you want to, or array, you want to update it. So what will you update it with? The previous value that you see, the current value, with, since now Y is in the tree, so from S you come to Y and then you hop to U, right? So what is the cost of this? So delta S comma Y plus the weight of Y to U. So if, I mean, since y is now a new addition in the tree, the driver can come from S to y and then take a outside edge, right? So is that route more, is it shorter than the route that was known before? So if it is shorter, then you update delta in that location. So clearly in all these locations, or not clearly, but you have to verify this, that this means that in these locations, delta has been corrected with the respect to the new tree. So this is now with the new tree. Right, so this is the delta function that is now correct with respect to the updated tree T. What about the other? Yeah, so the thing is that is automatically removed. It's a good point. So it will be automatically removed because whenever you call delta on some vertex, that vertex is outside the tree. So when you move y from undiscovered to the tree, then this delta will never be actually used. In the future, it will not be called because you are only interested in outside ones, undiscovered ones. But still, we have to make sure that the delta on the undiscovered ones is correct. Okay, so that's the thing you should be convinced about here. So delta on new u is correct. Just check this. Okay, so the tree is updated, the delta array or heap is updated, and now I think we can safely move to the next iteration. So now we go to the next I and so on. So with every iteration, the tree grows, delta array gets corrected, and ultimately tree becomes everything. That's the shortest path tree on the graph G. So that finishes Dijkstra's algorithm and pseudocode. Okay, any questions? Yeah, so this is basically coming from this idea number 2 that we had of shortest paths and this formula for delta of u that we had. But in the pseudocode, you have to carefully check that it is achieving what we claimed before. And finally, we have to do the time complexity analysis. So this is extract min here. So extracting the min delta from the heap is extract min. Then you, how do you move y? Okay, that is not with the heap. So that is just, you just delete y from u and add it to t. Finally, in this delta change, right? Here you are again changing the heap. So how is this change happening? So delta u value is being decreased. So this is decrease key. So these are the calls to the heap, function calls you are making to the heap. So that will determine your time complexity. So how many extract min are there? N times, 1 per iteration. And how many decrease key are there? Yeah, 1 per edge, right? So size of E, which is M. So N here is size of V. That many extract min and edge many decrease key calls to the heap. Yes, so these things are kind of optimal. You cannot reduce this. So every edge has a weight, right? So all those weights have to be seen. So M decrease key call seems minimal, and then N extract min also seems to be minimal because, well, you want to find distance from S0 of S0 to V for all the vertices. So you cannot really minimize any of this. This is already the least possible. What you can do now is deduce the overall complexity from here. So using binary heap, gives how much time? Yeah, so extract min is well, n log n, and decrease key is also m log n, so m log n. Is that clear? So this is the time complexity using, so this is now self-contained algorithm. Everything that is in this pseudocode you have seen in the course. Right? So if you implement this course algorithm, then you will get m log n time algorithm. How does it compare with our easy algorithm that we saw before? So what was that? N square plus m. Yeah, so there the dominating term was already n square. So you have to compare this with n square. So, well, if there are many edges, like n square edges, then obviously m log n is actually a slower algorithm, right? Then you should use the n square algorithm, which was the easier one, written in the previous class. But if the number of edges is much smaller than n square, somewhere between n and n square, right? Then this heap algorithm will be much faster. Right? So depending on whether your graph is dense or sparse, you can choose one of these algorithms. Well, but this is not end of the story. So you can use cleverer heaps. So that is the theorem we will not prove here. But this is Dijkstra's algorithm. Finally, that if you used Fibonacci heaps instead of binary heaps, then the time complexity will be paths with positive weight. So what is the fill in the blanks here? No, I think decrease key was O1. So if you use Fibonacci heap, then everything is constant time except extract min. Extract min remains log n. So you get n log n plus m. So that's the time complexity, which is much better when your m is more than n. Okay, so if your m is, let's say, n to the 1.5, so it is somewhere between n and n square. So n to the 1.5, both those algorithms that you have seen before are slower, while this guy will give you something much faster. Okay, so there are multiple options. So depending on what is your input, you can pick any of these. But I think the this final one is faster than everything. Yeah. So this third one is the fastest in all cases. So this is the final theorem, but you have not seen Fibonacci heap, so you don't know all the details. But with the heap change, you can achieve the best. So this essentially is the best algorithm in the last, even it has stood in the 70 years. Okay, so any questions? So if no questions, then we have very little time left in the semester. So we can start the last topic, which is back to sorting, but linear time sorting algorithms, okay, instead of n log n. So we can finish up with that. So can you sort in linear time? So this merge sort or average case quick sort that you have seen, and also heap sort you have seen. So let's write that. So insertion sort, merge sort, quick and heap sort. So for insertion sort on an array of size n, it takes how much time? Yeah, insertion sort is very basic idea. You look at the ith element and try to fit it in the previous sorted elements 1 to I minus 1. So it's basically 1 plus 2 plus 3 dot dot n. So that is order n square AP. So there you can't do much. The good ones are, so merge sort you know is n log n, that's the divide and conquer recurrence. And heap sort also, it is in a way even more elegant. You are just doing extract min in the heap every time. I mean, you first heapify your array, and once you have heapified in linear time, then you can do extract min. But you have to do extract min n times, so you get n times log n. Quick sort is a bit more confusing. So it is anywhere between n square to n log n. And may even be order n. So there is a whole spectrum for this because you are not specifying the pivot. So for a randomized pivot, the time could be anything between linear to quadratic. But average is, you can calculate the average case, that is n log n. Okay, so for a random pivot, it is actually n log n. So this is what some people use in practice. Question is, can we do faster? Than n log n. And the answer is it possible to reduce n log n? So in general, it should not be possible because if you have an element x and an element y, such that in the array somewhere x and y appear in the wrong order. So say x is less than y, but x appears after y. So x is less than y, and in the sorted order it should have been flipped. And this is your array going in that direction. So when you want to sort in ascending order, x and y have to be flipped, right? So if you think in terms of pairs, how many pairs there are that need to be flipped? So by that count, you will get n log n as a lower bound. You cannot do better than n log n. So what is the number of inversions? So you can analyze via a number of swaps or inversions. So essentially, how many comparisons were made? How many comparisons x compared with y, and then there was a problem, so you had to swap. So how many such operations are needed? You will see that in the worst case, you will need that many n times log. You cannot really do this in linear time. Okay, so there cannot be a general sorting algorithm faster than this. But we'll finish up the course with some special cases which are actually very practical problems, where the idea will be to go inside the integer representation. So only look at the sorting of integers, and don't stop at comparison of integers, but actually go inside and see how the integer looks. Okay, so use the integer representation in more detail. That is how we will make this faster. So it's not just a comparison thing, but we are actually breaking up the integer and seeing its pieces or its digits. So the problem we are looking at is, you are given an array A of integers that are small. Okay, so n integers are given that are between 0 to k minus 1. So you can think of k as 100. Okay, so you are given, and n you think of as billions or trillions. So you are given a lot of integers, but they are all small integers, and you want to sort. That is the question. And almost all practical questions are of this type. So we want to make this faster. So how fast? We want to do this in linear time, so n plus k time. Okay, so obviously if the integers are very big, then that will contribute in the time. But suppose the integers are not that big. Even if you assume integers to be maximum n in value, so you are given n integers, each has value less than n. Can you sort these in linear time? Okay, so this is a special case of sorting. And it's very helpful in practice because so helpful when integers are small or you can call it integers are bounded. For example, your roll number or your date of birth, these will not be very big, right? And usually in practice, we only sort those. I mean, also your marks in exams are very small, right? Both literally and figuratively. So these things are what we are sorting. So this is, almost all practical examples are like this. So date of birth, roll number, marks. Grades are extremely small. I mean, grades are just from 0 to 10. Yeah, it's usually closer to 0. So these are the numbers. So K is extremely small, but N is very large because number of students or number of citizens is very large. So N is much, much bigger than K. Okay, so I think we'll not be able to start, but there are two algorithms we'll do. First we'll do is counting sort. For this problem, this input output. So counting sort is a very basic idea here of instead of focusing on sorting the numbers, you just count their frequency. Right? Counting frequency tells you the sorted A also. So count. Oh yeah, so before that I wanted to make the point here that K is small, these keys are small. But the associated data is not. So every student has other data like address or transcript or whatever. So those things are attached with the roll number. Right? So the data is actually very big, but the keys are very small. So what we want is actually we want to sort according to the keys, but even the repeat, so there will be many, many repeated keys, and the associated data should be kept with that, right? So we'll be focusing on that. Let's say if in the array two students have the same marks, so student 1 appears first in the array, student 2 appears somewhere later in the array. When the array is sorted, we want student 1 and student 2 to appear ultimately in the same order as they were present in the input. So which means that student 1, even after sorting, should appear before student 2. Okay, so their keys are equal, the grades are equal, or marks are equal, but we don't want to swap them in any operation. Okay, so this will be an important point in counting sort. So count the frequency of the keys. Use it to output the sorted array. Extra point is that without swapping equal keys. Okay, so this is the point of stability. This is what gives you a faster algorithm, that we will try to minimize the swap. Okay, so if x and y appear in the array, x before y with a gap, if their keys are equal, in no situation will we actually swap them. So we want to do minimum swaps. This is called stability.